Good evening, everyone. We'll wait a couple more minutes before starting. I think people are still joining, but hope you can see my screen and hear me clearly. Great. Okay, let's get started. Good evening again, and welcome to the week 3 live session of this course. Yeah, let's get started. So, for anyone who is attending this for the first time, a quick recap. So we have two live sessions that are conducted every week. One is Monday 7 to 9 p.m. and the other is Sunday 6 to 8 p.m. Both are conducted by different people. If you have the time and are interested in attending both, sure, feel free to. If not, you can always pick one of your choice based on your convenience and your availability. And what can you expect from these live sessions? They will heavily focus on problem solving and will be aligned to that week's course content from NPTEL. Again, the problems that we discuss will be very similar to your assignments, and they're intended to help you solve those assignments. And this is intended to be an interactive session, so feel free to bring any doubts or questions that you have broadly over that week's course content. But in case you have some doubts from previous week's content as well, you can ask it here. And since we have a large audience, we will limit the interaction to be through the chat box. So post your questions or doubts anytime. If I'm in the middle of something, I might get to it 5 minutes later, or if we run out of time, I might address it in the next session, but I'll definitely make sure and address it. And post the session, you will receive access to a sheet. I think you've already gotten that. So there you can find both the slides and the recording of all these live sessions. So don't worry in case you end up with internet issues or you have to drop off and rejoin and things like that. Yeah. So broadly, this is a 2-hour session. So we'll go with a 45-minute recap followed by 45 minutes of problem solving, and the last 30 minutes would be for any doubts and questions. And we'll have a 5-minute break around 8 p.m. And don't hesitate to ask your questions, whatever they are. And if you want more explanations on something or even some meta questions, right? For instance, one of the things we discussed last week was how to read a research paper, which is not really part of the course as such, but it would help you understand the course and maybe go beyond the course a little bit. So I'm open to any suggestions and feedback that you have on all of that. So feel free to ask, right? Even if it is something like I don't understand this whole concept or this whole topic, feel free to ask, and I'll do my best to present it in a more accessible way. Since this is a postgraduate course, it will touch upon a lot of concepts, sometimes without going into too much details. A perfect example is your week 3's networking, right? A lot of concepts are covered, but repeat the part about reading research papers. So since the video is on YouTube, I would recommend that you go through it. It is there in the first part of last week's video. In case you still have particular questions on any of those aspects, right? For instance, let's say you tried reading XYZ paper and you couldn't follow whatever was mentioned, then ask me that and I'll again repeat it, because we have 2 hours, right? I don't want to cover 10 minutes over the same thing again. Since it's there on YouTube, you can always go back and watch it. It's in last week's session, week 2's live session. Yeah, sure. So that's about the logistics of the live session. Hope everyone got that. So where do you find the recording? So let me just see if NPTEL has shared that with you. Yeah, so in your course tab, I see a problem solving session recording, right? So if you click that, it will take you to an Excel sheet where you have both the YouTube link and the presentation folder. So this is on the leftmost tab where you have things like week 1, week 2, week 3, week 4, right? Below all of that, you will see a heading saying problem solving session. If you click that, you will get access to the Excel sheet. Yeah. Okay, any other questions before we move on to last week's doubts and questions? Okay, if not, let's move on. So I think last week we didn't get a lot of time to go over Kubernetes, and some people said that it would be useful to go through it in a little bit more detail, right? So we'll try to do that today. Again, I've not put in too much information into the slides themselves because I think Kubernetes was discussed in week 3 as well. So we'll start out here and then look at some of week 3's concepts too. So broadly, I think you guys remember the difference between a virtualized deployment and a container runtime, right? The broad takeaway is that containers give you reasonable isolation at a very minimal performance overhead. So again, I think I mentioned this earlier, but containerization can be used for different purposes. One way is the first thing that is mentioned here. It's a good way to bundle an application along with its dependencies, right? So this is typically called something like application packaging. The other reason you would want to use containers is multi-tenancy with some form of resource partitioning. You can always run multiple processes on your system, but that would not give you a good way to partition resources. With containers and some of the features that they come with, it's easier to partition resources. For instance, you can say spin up 2 containers with 2 CPU cores each, right? Something like that is possible. So that's the second reason why you would want to run containers. The third reason could be wanting to run different processes with some level of isolation between them, right? So these are 3 slightly different reasons you would want to run containers, or your reason could be a combination of any of these 3, any or all of these 3. So now this is about containers, right? Now coming to Kubernetes, which does a lot more things in addition to just spinning up a container. So one of the examples that I think you saw with the demo is if a container for some reason goes down or is no longer accessible, another container needs to be started, because like I was saying last week, as a user you don't care about all of these logistics, right? You seldom want to know why the container failed or what might the error be behind all of this. All you care about is that if something goes down, another one is automatically started by the service that is giving you this, right? So Kubernetes does this and a lot more things like this. So broadly, it manages the containers that run the applications and ensures that there is no downtime. And you'll see some of the other features as we go into week 3's lectures. So we'll move to the next thing. So the other thing we saw is about a Kubernetes cluster and the components of these clusters, right? So one is what is called a control plane, which you see here, and the other is what is called nodes or worker nodes. So broadly we saw that the control plane coordinates the cluster. The nodes are the workers that run applications, right? Now so this extra information that I put in on the right is from this link. So wherever I put in extra information that is not on your slides, I typically give you a link in the slide itself, which you can go and read. I try to make sure that the link is not very dense reading material. It's typically very accessible, right? So if you read it, you will understand what these things mean. So this is from the official documentation of Kubernetes, where you can read if some of this terminology seems very obscure to you, right? For instance, one of the questions we got maybe last week or the week before that is, what is a node? Is a node a physical machine? Is it always the case, right? And I said it depends on the context. For instance, a node could also refer to a virtual machine, right? So it's not really necessary. So for all such questions, the documentation would be a good place to find answers. So let's look at this extra information. So coming to the worker nodes, they host the pods that are components of the application workload. Whereas the control plane manages the worker nodes and the pods, and typically in production environments, the control plane runs across multiple computers. So why would this be? Think about it. So if in this diagram, for simplicity's sake, you see a single node or a single machine representing the control plane. Now if you run this on a single machine, just the way a worker node can go down, the control plane itself can go down, right? So how do you prevent that? Usually by having some form of redundancy. Basically you have the control plane running across multiple computers, so that even if one of them fails, there are backups, there are backup control planes that can take over, making sure that your cluster is managed and the applications keep running, right? And similarly, a cluster usually has multiple nodes, and yeah, this is what it's talking about, right? Fault tolerance and high availability. So you might have noticed with some services, right, occasionally maybe you see a downtime with WhatsApp, right, and it might be even half an hour, but millions and billions of people complain that, oh, WhatsApp is down, I'm not able to send messages, I'm not able to do that, not able to do that, right? Similarly, so as a service provider, the primary intention is to have high availability and fault tolerance. So high availability is, so you can look up these terms. Again, these are very commonly used in systems, right? Fault tolerance, availability, persistence. You can look these up. So this basically tells you how resilient a system is to failures, and how much of the time you can actually access the service, right, regardless of what happens behind the scenes. So that's about the control plane. And a little more detail about the control plane: it makes global decisions about the cluster, for instance scheduling as well as detecting and responding to cluster events. So like this, for instance, starting up a new pod when a deployment's replicas field is unsatisfied. So all of these things are done by the control plane. So this separation is kind of logical and physical. So the nodes handle the application's work itself, and the control plane handles things that are needed for these applications to run. So it's like a management thing. So you can think of it as the applications and the OS, except that I'm running these on different nodes. Why do we do that again? Because typically you want a dedicated hardware for the control plane, and you want your application to run without facing interference from this, right? But that need not always be the case. So all of these are defined as logical entities. How they are manifested physically on hardware depends on the configuration. For instance, you might set up all of these on a single machine just to understand how it works, and that might be possible, right? So that's perfectly fine, but this is just typically what happens. So typically the control plane spans multiple machines. So I think that was the only question I had from last week. So let's move to week 3 and a quick recap. So before that, any other questions or concepts from week 1 and 2 that you felt was difficult or confusing, or that you still don't have clarity about? Anything like that? And how is the course going so far? So you're almost at 3 weeks out of 12 are done, right? So you're 1/4 done with the course. So how does it feel so far? Does it feel too difficult, or do you think it's okay, manageable? Just trying to get a sense of things, not trying to do some assessment or evaluation. So just how are you finding things? Difficult but interesting. Okay, that's good. So whenever you learn something new that's relevant, initially it often feels like that, right? It's difficult, but then there is some level of interest that keeps you going. Yeah, everything is explained briefly. That's one of the problems. So I completely agree. That's what I was mentioning at the beginning as well. But a postgraduate course is designed to be exactly that way, right? So in your undergraduate course, people typically come with a very narrow syllabus, and they cover that completely. But in a postgraduate course, what is expected of you as a student changes a lot. So people give you an idea, a skeleton of what the various topics and the various um they give you an idea of the breadth of the field, and this is kind of an appetizer. It is expected to provoke your interest, and then you are expected to go read up, right? Although a lot of Indian universities may not conduct postgraduate courses this way, typically this is how it is done, right? That's why in India, for instance, a lot of times we take 4 to 5 courses per semester, postgraduate courses, but you'll notice a lot of universities abroad having 1 or 2 courses per semester, and that's because for every hour that you take, you could be expected to put in 4 to 6 hours on your own trying to catch up with the material. So that is something that you will have to do in this course, and due to the time limits, right, you have 5 or 6 lectures of 30 minutes each, so there's not much that people can talk about in that time. So you will have to do that reading on your own, and then once you do that, you can always ask. But the problem even with a live session is, for instance, if I took that networking session and then I went into each of those concepts, it would take me at least 3 or 4 hours. So that's the difficult part. Anyway, let's see the other responses. Electronics background, that's interesting. Again, you will probably resonate with more of the physical layer and the eye diagram and things, communication oriented things like that. So depending on your background, each person might kind of resonate with different topics in this course because it's a multidisciplinary course. Somewhat difficult to replicate the hands-on projects or lab work. Yeah, that's another thing, right? So some of the demos might be on some HPC cluster or some particular hardware like BGX, and they are intended to showcase specific use cases. For instance, you saw a demo of load balancing, but if you want to just use Docker to say deploy an ML application, you don't need to do all that, right? So take from the hands-on that you see specific points that you want to do, and again, a lot of these things will have videos talking about how to install them and things like that. And if you face any issues, you can always ask on the Google forums, and it's a best effort thing, right? NPTEL courses again are not very tailored for hands-on. They are tailored for understanding concepts and application of those concepts, because it's all mostly MCQ evaluation. So yeah, that's something that you can probably give as a suggestion in future if you'd like to learn hands-on of some of these, and that would be good. Lab explanation, right? Content is really good and vast, more theoretical approach, difficult to realize practical implementation. Some of the that's what, again, it's a very interdisciplinary course taught by people from very different backgrounds. For instance, the person who did the networking series of lectures was somebody who used to work in Mellanox and now works in NVIDIA, and this sort of networking is their bread and butter, right? So it's explained from the perspective of somebody who would want to do that, which might not apply to all of you. But again, there might be parts in the course, for instance, the containers part, the Kubernetes part, the PyTorch part, that might be universally applicable, and all of you might take away things from that. But that doesn't mean that something like networking is irrelevant, right? It's again something interesting to learn. It might not find application right away in your career or in your education, but it is something useful as long as you broadly work in this domain of accelerating machine learning. So yeah, so if you're looking for specific things, again, focus more on those things, right? So what you want to take away from this course is different for every single person, and that's why I try to cater to a wide variety of audience at various levels of expertise. So you can always be selective about what you put a lot of your effort and attention into. Anyway, yeah, so week 3 and 4 is typically when we see a lot of people drop off. So I think there were 50 odd people in the very first live session, and today I think it's down to 15. So yeah, but the people who are finding it interesting and useful, I think if you stick around, you will learn something out of this course. I think it's one of those courses that tries to teach you a lot of things. Yeah, do you have a question? Hi. Hands-on project at the end of the course, not as of what I know. So typically NPTEL online courses don't have things like that. I don't know if you were told that this course would have. So sometimes courses have some sort of programming assignment, just one or two. But again, I've not seen a lot of courses have that. Several courses have just MCQs. So I'm not very sure about this. But in mostly there will not be a hands-on project. But you can anyway double check that on the Google group by asking. Syntax of the exams. So that so far, going by the question so far, so broadly your assignment questions are a template for the exam questions, right? So whatever sort of questions you see in the assignments and the live sessions will be the questions that get asked in the exams. Now again, I haven't seen a lot of numericals so far, so I would agree that they're mostly theoretical and they test your understanding of either a definition or a concept or something that was not directly covered in the lectures. Now the first and the second parts are easily doable, right? If you follow the content of the lecture and if you go through those things, they will help you. But the third category of questions, which is things that are not directly there in the slides. For instance, today we'll see some of those questions, right? Which again, the topic would have been covered in very little detail, but you might be asked about something that goes one level below, right? Those are the tricky questions in this subject, at least with respect to the NPTEL exam. So for that, you need to kind of look at other resources that are there in the slides, also look at things that are discussed in the live sessions and try to answer those too. So MCQ or theory based? Well, you can have theory based MCQ. So I don't understand what you mean when you say theory based, right? So if you mean subjective questions, no, it typically is MCQ questions. The MCQ itself can be numerical or it can be something that's theoretical. NVIDIA internship opportunities, I don't think so. I am not sure if you were told something like that, but as of what I know, not really. Yeah, so I think that's all the questions. Okay, let's move on then. So this week again, broadly there were two forks. One is the DPops, which continued with Kubernetes and Slurm, and then started off with your DevOps, MLOps, and went to DPops. The other fork was networking for HPC, which was again lots of things were covered there, and depending on what background you come from, you might have found it very, very intimidating, or you might have found it very interesting. But it's a kind of end-to-end view, right, across various layers, which you rarely get. So it's a very unique perspective to the whole networking for HPC, in my opinion. But again, feel free to point out if you have things that you didn't understand or you want more information. So we looked at things like the physical layer and fundamentally in terms of physics, what are the limitations that you have. And then we moved on to the network layer and routing, transport layer, things like RDMA, then a lot of advanced technologies, intelligent networks, resilient and self-healing networks. So this was week 3. Now we'll go into a quick recap of some of these concepts and then we'll move to the problem solving session. Okay, so yeah. Okay, how are we supposed to pivot this course into a job or career opportunities? So if you're looking at something like, so again, when it comes to jobs, right, there are a variety of AI and ML positions or job descriptions available. Now, there are a lot of companies that look for deployment of AI or ML, right? And this deployment could be on the cloud, it could be on the edge, and there you are expected to know both machine learning or deep learning and the system side of things, for instance containerization and things like that. So those, knowing these things will definitely help you in the interviews of those companies. But again, all of those roles will typically expect hands-on experience, or in the form of some project or some demo that you have, right? So if you ideally take an AI or ML course, I'm sure you would have done some of these projects, right? Simple things using some machine learning paradigm, or for instance you could have a deep neural network, right? And let's say you took this and then maybe you deployed it onto one of the edge devices that we discussed, the Jetson class of devices. So and then let's say you did some optimizations. That could be a good example of an application of all the systems things that you learned in this course. The other kind of project that you can have is something that just builds an application. So take a particular DNN, figure out what you want to do. First figure out what you want to do, then figure out the data set, the DNN for it, and then do that, right? So those are different projects that you can have in your portfolio, and that is needed today, right? Because not just people don't just care about your theoretical understanding of all of these things, they want you to have demonstrable practical experience. So that is something you'll have to do in parallel with this course. But again, that is for a particular class of jobs. For another class of jobs, you might need to know a lot more about the model itself, right? The architecture. For instance, if you say a deep neural network, how is that different from other ML paradigms, or start from a linear regression, go to some multi-layer perceptron and things like that. So basics of ML or AI course will teach you some of those things, and that's again a different class of jobs, right? So depending on what you want to do, this course is like a foundation that helps you no matter which of these forks you take. But I would strongly recommend trying to do something hands-on in parallel with this course, like a simple project or something that you can talk about, right? And you can find a lot of ideas on the internet, and you can also find a lot of starter code. For instance, if you are looking at using a certain model, you will find existing implementations of it in PyTorch or whatever framework you're using, right? Typically PyTorch or TensorFlow, which is a good starting point, and you can try out those things and then decide what you want to do. What skills can we add to LinkedIn once we complete the course? So let's just look at week 1, week 2 and week 3, right? So you would probably say, so let's just look at this one, right? So again, some of these things depend on, so for instance, if you put Kubernetes, typically you might be asked, how did you use it in a project, or where did you use it? So theoretical knowledge again may not be enough, but you can always put things like Kubernetes or Docker containers. You can also put deep ops and maybe networking for HPC, right? So broadly you can put it as maybe deployment of machine learning, or accelerating, as the course title says, right? Accelerating artificial intelligence. Or if you go deep enough into some of these things, you can always list them individually also, right? Things like OS, architecture, networking, all of these things are things that you learn. So, but again, be careful that you put something that you know enough about. Don't put all the keywords that you have in the course, which makes it sound like you've studied 20 subjects, but in reality it's a little bit of each of those 20 subjects. So that would be my suggestion. How will it help for managers? Again, already have 10 plus years of experience. Again, some of the newer technologies that you might probably be coming across, you might find it in this course. Other than that, again, it largely depends on your team and what you work on, but I would say you would find interesting directions to look into in more detail. So you could for instance, in this networking part, let's say you came across RDMA or GPU Direct or one of those things, right? And that could be a starting point to explore something that would make your existing project a lot more efficient or a lot more easy to deploy or accelerate in terms of performance. That's one thing I can think of, but without knowing the specifics, it's hard to answer that very accurately. But again, if you're interested in learning some of these things or switching to this domain, again, that could also help. But if you're already working in IoT, I think you would have seen a lot of the sensing and the communication and things like that. So this might maybe exposes you to a little bit more on the edge GPU side, or maybe on the networking or things like that. Open for mentorships, again, that's a very broad term, so I'm not sure what you're looking at. So from the perspective of NPTEL, this is not intended to be anything more than a live session, but if you have particular questions or particular things that you need help from me, on a personal level, I might be able to do that, but that again depends on the time commitment and what you're looking for and how good a fit I am, right? So feel free to write to me either on LinkedIn or on my email ID that's probably mentioned in the first slide, and then if I'm able to do that, I will get back to you. But that then again, I want to clarify that it is me as a person, not me as an NPTEL TA. Yeah, so that's the end of the questions, I think. Hope that helped at least some of you. Again, there are a lot of questions from a lot of very different people, so this is just my opinion, right? Feel free to disagree with it. Okay, let's move forward. So some of the Kubernetes terminology, right? I don't know how visible this is. Maybe one thing I can do is to quickly zoom out a little, zoom in a little bit on this. Yeah. So kubelet, again, I think you've seen this term before, the agent that runs on each node and is responsible for making sure that the containers are running. kubectl, again, you looked at a lot of kubectl commands, so you probably figured out that this is the command line interface, and you might see Kubernetes written as K8s. That's one of its alternate names, right? So this is broadly the CLI. And manifest, again, I think you looked at that YAML file that had various parameters, right? So you can configure Kubernetes by editing these manifest files. So they basically have metadata, right? And they're typically written in YAML, but they can also be written in JSON. And node is a server in the Kubernetes cluster. It, again, server is, node is a very umbrella term, right? So it can mean different things at different points. Always think of the context before you associate something with it. Pod is the smallest Kubernetes object, and it represents a set of running containers. Job, a finite or batch task that runs to completion. I think this is very, very straightforward, right? This is okay. Replicas, replicated pods in the cluster, Kubernetes will maintain this amount if failures occur. I think this also was mentioned in some of the earlier lectures. So this is again one of the features of Kubernetes, where it goes above and beyond just running the application, right? So if a failure happens, it makes sure that your replicas, whatever you specify as the replicas, is maintained. Secret, it's an object to contain passwords or API keys. Service describes how to access applications. Deployment, object that encapsulates an entire application. So these are some of the basics. Yeah, so again, I think we saw some of these worker node and master node, right? So it's, yeah, and coming to creating a job, you could either do it through the UI or through the CLI. So these are different ways of accessing the same API, right? I think even for Docker, some of you had this question that if I use the UI, is it okay? It's okay. It's just that there are different ways of doing the same thing, and typically as a programmer, CLI is always the preferred one, because UI abstracts some of the things from you, right? And as a user, that might be okay, but when you're trying to learn more about the system software itself, then CLI would be the best idea, because you might see a lot of flags and a lot of custom options that you may not see in the UI, right? So CLI is a good way to get familiar with the tool, and I would encourage you to try out everything on CLI, even though it might add some level of complexity. And yeah, so these things I think are all repetitive. The notion of a pod, the notion of a worker node, master node, right? So we'll skip that, and this is again the same as what we saw last week. So you have Kubernetes and you have Slurm, and Slurm, while it handles a lot of multi-node jobs with dependencies, workflows and DAGs, and does some scheduling and reservations, it does not do other things that Kubernetes does, right? Like analytics, monitoring, and Kubernetes also, you can also share nodes, schedule jobs for GPUs on a node, etc. And this also covers data permissions and security. Okay, as a UG student, what are the projects that I could do with Kubernetes? Off the top of my head, I am not very sure. With open source resources, I think look at what you want to do on an application level first of all. So you could do this in two ways, right? One is to come up with a problem statement. Say that I want to do this, and see whether that problem statement requires you to use Kubernetes. So that may or may not, and that's okay. If you specifically want to do something with Kubernetes, then you could go ahead and look on the internet for various maybe AI or ML projects that use Kubernetes, and that would give you a starting idea for what's a good use case for Kubernetes. And after that, you can always customize the problem to something that you want to do, right? So I don't have any one line ideas at this point saying you should do a project which does XYZ, but I'm sure you can figure that out if you do a quick Google search. And again, maybe do it incrementally, right? So first thing would be to just try out various commands, various features, and then look at a very toy problem and start off with that, and then add more complexity to it, and then you kind of build up. That's again something, as a UG student, that's again something that would help you handle something that's very high level and that seems very complex, right? You progress towards it in steps. So yeah. Okay, moving on. So DevOps again, if you worked in the industry, I'm sure you would have come across the word, but if not, it's basically a short form of development and operations. So as you can see here, when you develop something, you have the planning aspect of it, you have the coding, the building, the testing, right? And the operations aspect of it is the releasing, deploying, operating, monitoring, right? And this is like a continuous cycle of things. So this is, why is this needed? It's needed because this is like a pipeline, right? In industries, you might have heard of this whole thing about release. For instance, I'm sure a bunch of you use Windows as an operating system, and you would have seen Windows updates come through every couple of weeks, right? So for any company to periodically ship software in production and keep it running reliably, they need to have such a pipeline. It's like a production line, right? So they clearly know what to do. Someone makes a change, then they test it out, then they release it, deploy it, monitor it, right? So it's a full cycle that needs to happen. And also, by having tools that do this, as a developer, you need not care about all of this. You just do your part, write the code, and then this whole thing kicks into motion, and it takes away the complexity from you, right? So you just need to solve the problem. The rest of it will be taken care by these DevOps tools. So they do use a lot of automation and well-defined workflows to do this. So this is the broad idea. This is not ML specific, right? It applies to any piece of production software. Now, coming to MLOps, what changes? So it's not just code, it is data. And why does this matter? Any of these could change, right? So if you look at the training process, it's basically code and data that gives you a model. And again, both of these could evolve independently. So you have two lines to kind of indicate that. So, and since data comes from the real world, you can always have more and more data or different data coming through, and you have no control over how that changes. And these are evolving independently, as in the data is not tied to the code is not tied to the data. So the common thing is just the time. So in MLOps, you want to kind of create a bridge between these two planes in a controlled way. You want to have some amount of versioning with both data and code. That's the idea. And again, here you have this notion of training and inferencing or serving, right? So at the end of the training, your output is a model, and this model acts as the input for serving or inferencing, and the output of this inference pipeline is the predicted output. And so to this training model, you take the code of the training pipeline, you also take the data, and you might do some transformations, right? So for instance, if you've worked with vision models, you might see something like cropping. So let's say this is your image. So I might do something called a random crop, which means that I crop, let's say, this much of an image, or because it's random, it could also be this, it could also be this, right? What does this accomplish? It makes your model robust to which portion of the image I pick, right? So there are a lot of transformations like this that could happen. Again, this example that I gave is specific for vision. Your data could be video, it could be audio, it could be text, it could be images, right? So lots of transformations are possible depending on the type of data and the model. So then you transform the data, the training pipeline takes this data, takes this code and produces a model. Then the ML pipeline takes model, takes the code that's needed for inference, and takes the inference data, and then gives you a predicted output. So again, CI/CD is a common term, refers to continuous integration, continuous delivery or deployment. So this is the uniqueness of MLOps as compared to DevOps. So you can see a lot more complexity coming in because of the nature of ML, right? So there's training and inferencing, there's code and data. So this brings in some amount of complexity. Now moving on, so we are moving into the second part of week 3, which is the networking for HPC. So typically you had SMP machines or symmetric multiprocessing, right, where you have multiple CPUs and a single memory unit. And as was discussed, so this is also referred to as shared memory systems. As you can see, there is one unit of memory across all of them. But there are some disadvantages to this and some advantages, of course. But eventually, when you want to scale out, this can become a limitation, this way of having connection between CPUs and the overhead to communicate between those CPUs and accessing the same memory and things like that. So then we move on to the modern day supercomputing clusters or HPC, which is again, which can be generalized into message passing systems, which is more like saying they are distributed systems. They no longer share memory, right? So think of your system and maybe your desktop and your friend's desktop both connected to the same network switch. So both of you have your own CPUs, both of you have your own memory, and the only thing is you're communicating over the network, which is a form of message passing, right? So that's the fundamental difference between shared memory systems and message passing systems, and that's also their evolution. So again, these concepts will move across a lot of domains, right? So I've tried to go into detail in some places, in some other places I've skipped because we don't have a lot of time. But if you think that something is relevant for you, or that you would like to learn more about this, then please post a message in chat as we go through these, right? So here we are looking at transmitting bits and bytes, and we have two things mentioned here: non-return to zero and return to zero. I think the return to zero is too small, so you can't see it. So again, I don't know if this difference was very clear from this figure, but broadly the idea is that after you finish transmitting something, there is no neutral state, right? So it's a 1 here, 1 here, so there's no gap between these two, right? It immediately goes to the next thing, and then there's a 0. So this is the non-return to 0, meaning that there is a signal value for 1. Let me call this as V1, right? There is a value for 0. So at any given time you only go between these two values. There is nothing else. In contrast, if you look at return to 0, after every data pulse you come back to a neutral value. And one thing about this neutral value is that it itself might be, for instance, V0. So in this example, if you see, so the actual data that you're trying to transmit is 10110010. So in a non-return to 0, every pulse will correspond to that data bit. So here you have 1, so it's a 1, it's the voltage corresponding to 1. It's a 0 here, again 1, 1, 0, 0, 1, 0. This is straightforward. Now return to 0 is slightly different. So for 1, you transmit that 1. So this is again shown for, so that it's aligned, right? So you transmit the 1, and after that you come to a neutral state or a 0 state, right? For an equal amount of time. That's always there, no matter what your data. Now next, you are transmitting a 0, so you transmit that 0 for half this duration, and for the other half you come back to your 0, return to 0, right? Similarly, you have a 1 here, so you stay high for half, you come back to 0, stay high, come back to 0, it is at 0, stay at 0, and so on, right? So this is the difference between return to 0 and non-return to 0. And coming to pulse amplitude modulation, again this one I think is intuitive from this figure itself. So as you can see here, the amplitude, so you have 4 different levels, right? So we are trying to represent 4 different things using 4 amplitudes. So this is one of the amplitudes, this is the other one, this is the third one, and this is the fourth one. So the amplitude of the pulse is itself modulated in so many different levels to convey the value. So on the decoding or the demodulation side, if I get this value, right, assuming I'm on the same y-axis, if I get this value, I know that it corresponds to a 3, 1, 1. If I get this value, I know it corresponds to a 0. So notice the difference between a simple thing like this versus this, right? Here you only have 2 levels. Here you have 4 levels, right? So the amplitude is modulated. That's the key concept. Again, we won't go into too much detail on these things because there's a lot here in this particular lecture especially. So we'll again go a little beyond what was covered, but not too much into detail. Okay, moving on. So this is again a very popular notion in communications. It's called the eye diagram, right? So it's a very visual representation of the data that you're sending at the time that you send it, right, at the transmitter, and how the receiver sees it, right? And the intuitive understanding of this is this looks like an eye, right? Hence the name eye diagram. Now if the eye is open, it means that there is a significant difference between 0 and 1. So it's easy to at the receiver end to detect what's a 0 and what's a 1. But if the eye looks something like this, right, very narrow together, then it means that it's hard to, the bit pattern has degraded or the eye is closing, right? So that's a problem. It means that your receiver does not see the signal the way you have transmitted it. So this is the intuition behind the eye diagram. Again, we won't go into a lot of this. In case you're an electronics or a communication student, you would have seen a lot of this in detail, and you might have heard of things like intersymbol interference and zero crossing and things like that. But yeah, that's not very necessary for this course. Again, coming to the physics of why this happens. So we were talking about the whole stack of things, right? So for instance, in the very first class, we spoke about the memory hierarchy, and I was telling you guys, so if you think about why is, let's say, a DRAM faster than a hard disk, then ultimately it comes down to the hardware, right? And again, hardware is an abstraction, so it comes down to the type of semiconductor or the storage technology that's used, and one level below that is physics, right? So ultimately everything comes down to physics. So this is again one of those examples. So why does this eye closure happen, right? So when the signal goes into the channel, there is this phenomenon of scattering or losing some amount of voltage, right? Forward voltage attenuation, and there is a formula for that as well. So that's one of the reasons why this happens. So that's just trying to understand why this is. Again, we won't go into too much detail because all these are very in-depth concepts in themselves. So for instance, people who have studied this as a subject will see the scattering matrices, and you'll be calculating this thing and things like that. So again, we won't go into too much detail on that. Moving on, so we looked very briefly at an InfiniBand switch, right? So I think mostly we looked at what is the latency it has, what is the bandwidth it has, and overall you might have noticed a very low latency, very high bandwidth, and you would have, so I just want to leave this as an open question. Again, it's not answered in the slides, but it is something that will help you appreciate the details of these things better, right? So just the way I said, why is DRAM faster than hard disk, you can ask the question, why is InfiniBand faster than Ethernet? So from the perspective of the course, all you need to know is that InfiniBand is used in HPC broadly because Ethernet is too slow, right? 1 Gbps or these days 10 Gbps is all that you can get. But for HPC, that is not enough. You want much faster speeds and much higher bandwidths. So that's one of the reasons why InfiniBand came into play. And obviously from the specs that you see, you can see that it performs much better than Ethernet. But why is that, or what is fundamentally different in it, is something I would like you to think about. So when you think about these things, when you have that curiosity, right, that's when you go read about things. So if I just gave you the white paper of InfiniBand and said, go read this 100-page white paper, I'm sure a lot of you will not do it. I myself would not have done it. But an easy way to find answers to some of those questions is to be naturally curious, right? So if you're told about a new thing that makes something faster or easier or more performant, the first question that should come to your mind is why? Why is that so? What enables that change? And what are the disadvantages to it? Things like that, right? So when you have that curiosity, you will be able to go look at the white paper, see, and it might not be very obvious. Like if you right now open the InfiniBand white paper, you might not really figure out why it's faster than Ethernet, but it will get you started. And sometimes those things take you on very different directions and you find out a lot more than you had hoped to. So always try to think of these questions, and I will leave some of these questions on my slides without giving you answers, right? So the idea is for you to go look it up and then maybe come back to me and say, I looked at this and is this the reason it is faster, or I still couldn't figure it out, or something like that. But I will not answer that immediately, right? So take that time to think about it. We already have one answer saying less protocol and optical fiber. I'm going to leave it out there. We will revisit this in the next lecture if some of you are interested. It's not mandatory from the perspective of the course. Okay, again, network topologies, right? So again, this was not discussed in a lot of detail in the lecture itself. So you were introduced to 4 different topologies: factory, hypercube, torus and dragonfly. Today we will look into, in our problem solving session, we will look into I think two of these a little bit in detail, and the rest, if someone is interested, we can look into. But these are again very carefully constructed. So the idea is, I think I have a link to one of these resources on network topologies, but the idea behind all of these topologies is, if I wanted to access a particular node, deterministically how many hops does it take, right? That is one of the metrics that you can look at. There might be other metrics, but this is a very simple way of looking at it, right? So maybe for a very simple abstraction, think of it like this, right? So let's say I have a particular, let's say this is your college, or let's say this is your college, and let's say this is your home, right? Now one way to get here is like this, which involves some vertex C. Another way to get here is D, E and then B, right? Another way to get here is, let's say, F, right? Now all of these are possible, but now if I ask you, let's say this route took you 2 hours, this route took you half an hour, and this route took you 1 hour. Now if I don't know which of these you will take, I also cannot tell you deterministically how much time you can take. I can always tell you that it will be somewhere between 0.5 and 2, but I really can't tell you about the time, right? And this is a very simple example, but in a lot of these high performance computing, we need a certain degree of determinism. We need to know how long it's going to take, or what is the path from one node to another node. Another metric you can look at is, if one of these links is down, is there an alternate path to that node? So a lot of metrics like this, a lot of thought, a lot of mathematical formulation. So if you look at slides about some of these, right? I think I didn't put in the link, but maybe I will. Again, this is not very relevant from the perspective of the course itself, but it's purely out of curiosity. If you want to look at what those are, this is a good one to go look at. And again, it's a very advanced one, so you'll see a lot of notation, lot of terminology, but that gives you insight into why people care about these things and what does it affect. So it's all very mathematically formulated, very mathematically proven. You can deterministically say that it takes so many hops to go from one point to another point, it takes so much time to go from one point to another point. So every single link, the entire topology is designed very thoughtfully, and these are not the only ones, right? So there are newer ones that the research community keeps on coming up with. But yeah, if you're interested, go take a look, otherwise this is optional. So okay, since we are at the midway mark, any doubts so far? Anything you want in more detail? I'll just pause here for 10-15 seconds. Okay, no questions. In that case, let's move ahead. I think I have 2 or 3 more slides of recap and then we'll take a break. So RDMA is another concept that you studied, right? So first of all, have explain about Dragonfly. Let's see if I have an example. I think one of your questions asked about that, but I've put in a very brief example. So we will get to that in the problems. And if you want a more detailed explanation, I can do that in the next session. Yeah. So coming back to RDMA. So first of all, have you heard of DMA? If not, go look up DMA because RDMA is very similar to DMA. The idea is definitely the same. It's just the remote part that is different. Basically, you do that access from a remote machine. And again, broadly, if you look at it from a very high level, there are a lot of things that are bypassed in RDMA. So you can see here the whole thing. Again, I don't know how visible this is, but you can see that a lot of the stacks or the steps are actually like the driver, the sockets, all of these are bypassed and you directly seem to be talking from the application to the application, right? So that's where the benefit comes from. So you have a remote memory read or write in addition to send or receive, and there is a bypass as we saw here, or direct user space access. So again, like we saw previously in the OS part of it when we looked at, right? So we said that some portion is kernel space and some portion is user space. Yeah, some portion is user space, some portion is kernel space, right? So here there is a kernel bypass. So you directly talk from the application. This kernel, the driver part of it, all of that is bypassed. So again, there is a full offloading for the networking stack, secure channel based IO. You can ignore all of that for now. So the advantage that you get as an application is that you get the lowest latency, you get the highest bandwidth and the lowest CPU consumption. Why lowest CPU consumption? Again, you bypass a lot of things, so the CPU is not at all involved, right? So that's why. And how does that help? If you have lower CPU utilization, the CPU can do other things, right? So that's what it helps with. So this is the idea of RDMA. Again, I will leave this question out in the open. So RDMA tells you that it gives you a performance benefit, right? Lower latency, higher bandwidth and lower CPU consumption. So what could be the downside of RDMA? Think about that, because most things, there is no free lunch, right? In systems, there is definitely no free lunch. Lot of things that give you benefits also give you downsides on some other dimensions. So for certain applications, that downside might be doable, might be tolerable, but in certain other places it may not, right? So it's always good to be aware of what are the downsides to something. Think about that. Moving forward, so this is GPU direct RDMA. So here when we spoke about things, there was no mention of GPU, right? This is all example of RDMA. So a practical example, I would have to think a little bit. Let me actually think and get back to you on that. I will do that. And I think we are slightly short on time today, so I'll either do it in today's session at the end or in the next session. So GPU direct RDMA. So here what happens? So again, remember a quick recap. There is this notion of a CPU memory and a GPU memory. Again, remember that this is all in discrete GPUs where physically you have a separate RAM for both of them, right? Now, so then what typically happens is you fetch some data from network or storage, you copy it to CPU memory, then you copy it to GPU memory. And similarly, once the GPU finishes processing, you copy back the data into CPU memory, right? So here again, there is basically two copies happening, right? The GPU copies data. So here what happens is the GPU uses something called a pinned memory buffer, which is allocated by the GPU driver. Now RDMA uses these pinned buffers for zero copy kernel bypass communication, and it's not possible for RDMA to pin memory allocated by the GPU, right? So there is some level of, if you don't understand all of this, that's fine. At a very high level, it means that GPUs allocate memory in a slightly different fashion, right? And it's not possible for RDMA to do whatever it does for this GPU memory, right? The way it does for CPU memory. So what GPU direct RDMA, so essentially what happens is GPU copies the data from GPU internal memory to the GPU driver system pinned memory. Then the user space needs to copy data between the GPU driver's pinned memory and RDMA's system pinned memory. So that's what you see here, right? You see two arrows going here. So the first one is indicated as 1 here, and then the RDMA system pinned memory, which is this 2. So the user space component will have to copy this data between the GPU's system pinned memory to this RDMA system pinned memory, right? That's an additional overhead that you have, and some more of the details may be in the GPU direct slides that you have, but that's the idea. And coming to these latencies, again it's a very end-to-end view, right? So you start with the cables, which can be either optical or copper cables, and you see how low it is, right? It's in nanoseconds. Then you move on to switches, and you see that it's a few hundreds of nanoseconds. Then you move on to the application level libraries, right? MPI or the frameworks, and you see that it moves a lot more. And again, as you can see in the last column, it could be a lot more than this number. So it could even go to milliseconds. This gives you an end-to-end example, right? Even though at the copper cable level your latency is this much, when you go to MPI, what is the latency you get? That's the effective latency you see, even though the copper cable might be doing this. So there's a lot of overheads added by both hardware and software which contribute to this. And again, a very similar thing that you should look at. So this is not part of your slides, but I've just put it in because again it's very useful to look at that. So if you look at L1 cache, right, it takes 0.5 nanoseconds, and similarly you have numbers for branch mispredict, L2, which we can all ignore. The next one we look at is memory reference. So notice how the L1 cache is 0.5 nanoseconds, whereas the main memory reference is 100 nanoseconds. Then again there are a bunch of things here, we'll ignore it. This one is probably relevant. Read 1k bytes from a 1 Gbps network takes 10 microseconds. So it's already moved from nanoseconds to microseconds. Then read 1 MB sequentially from SSD. That moves to 1 milliseconds. And then if you do a disk seek, it goes to 10 milliseconds. So you can see how across the memory hierarchy and the network, how the latencies vary, right? So this is again a useful thing to look at for perspective. That way it gives you an idea of the relative speeds of each of these. Okay, I think we anyway explained this in one of the assignment questions. Let me see how much more we have. Yeah, so the idea behind SHARP, or Scalable Hierarchical Aggregation and Reduction Protocol, as you saw in your course slides, if you had one server, right, which had to kind of gather data from all the others, that could become a bottleneck. So instead what you do is you move some of the compute to the network elements, right? So this is again very similar to the one of the other ideas we briefly discussed last week, which was computing in memory, right? So here you are talking about computing in network. So there is a switch here where the data anyway passes through. What if you use that switch to perform some useful computation, right? For instance, all of these three hosts send some data to the switch. So the switch can quickly do an aggregation. Let's imagine for a moment that the aggregation is a simple sum. So let's say these are 3 values, and the switch can simply sum it up because it has that compute capability now. And then it sends it to the next switch. The next switch again receives 2 of these values, which it aggregates, right? So this is a way of using hierarchical aggregation and reduction. It could also be reduction using the network elements itself. So in network, tree based aggregation mechanism and lot of other features, right? So there is a lot of HPC applications to doing this, to things like MPI, distributed machine learning, lot of those things. So you could do again a variety of different things. So all of these are different MPI functions: broadcast, reduce, all reduce. You might not know of them, but that's fine, right? So this is the broad idea behind SHARP. And this was, I think, a part of the self-healing or resilient networks. So if you have a link failure here, right, you should be able to find another path to go through the destination. That's a good example of resiliency. And we saw some more detailed explanations of oversubscription, of network bisection and things like that. But this is the overall idea, that even if one of these links fails, I should find a different way to go from my source to the destination. Yeah, so with that we come to the end of the recap session for this week. I spent a little longer on the recap today because there was so much of content, and I think there is still a lot of content that I have probably not covered. So I'll take up the questions on Dragonfly, example of RDMA in the next session, because I don't think we'll have time today. But any other questions you guys want to add to the list? Let's wait for 30 seconds to see if anyone has any questions or doubts in week 3. Application taken as digital twinning. Which application are you talking about? Is it something particular, or are you generally asking about a project or something like that? I didn't really get that question, so you might want to think about it and reword it a little bit. Any other questions or doubts? Okay, if not, it's 8:16 now, so we'll continue at 8:21. So I'll keep the call running, but we'll resume at 8:21. Feel free to take a quick break. Okay, welcome back and we'll continue. Please explain pod. Sure, I can do that in the next session as well. How to deploy a super resolution model on a Zinc FPGA. Not really. I haven't used FPGAs in a while now. I can look into it, but I'm not very sure I'll be able to help you. But I'll anyway note down your question and take a look at it. And if I find any links that would help you, I'll share them in the next session. Okay, with that, let's move to the questions for this week. Okay, I think the answer is obvious from here, but in case you didn't take a look at it, MLOps is a combination of machine learning, DevOps, data engineering. Your options are A, B, C, B, C, A, C, none of the above. Any answers? Yeah, please use the chat box. I think I saw a raised hand, but it's very hard for me to track it. So option A, which is A, B, C. Anyone else? Yeah, so that's an easy one. It is A, B and C, and this ought to have been on the next slide. Sorry about that. But as you can see, it's a combination of all three, right? And there are various features that each one of these provides. For instance, DevOps gives you code version control. Data engineering gives you some form of data lineage and code version control. But in MLOps, you have code version control, data versioning, model versioning, right? And all three are linked so that you can reproduce results. So on a particular combination of these three, you might get a certain accuracy, right? So you need to have linked all of these three, not just maintain separate versioning. So that's one example of a feature that's a combination of all of these. Please use the chat box in case you have questions. It's hard for me to otherwise follow. Thanks. So it is a combination of all three, right? There are a number of features here to explain that. But let's move on in the interest of time. How does Kubernetes handle a sudden breakdown of nodes? Using node port service, using scheduler, fails to handle, using load balancing. Any answers? D, load balancing. Anyone else? D, okay. D, D, okay. Everyone seems to be sure of it. It is indeed D, and I have not put in a lot of explanations because I think you saw a demo, right? That was very convincing. For instance, you killed one of the containers and it automatically brought up another node, right? And it kind of load balanced the existing tasks across two nodes instead of three, right? That's a form of load balancing. So the very simple idea behind load balancing is if you have, let's say, 3 nodes, or let's say 4, right? And you have maybe 3 tasks on each of these, right? Now it is load balanced. All of them have equal amounts of work. Let's say one of them goes down. So now you need to redistribute these 12 such that all of them have the same amount of work, right? You can't take all 3 and put it here and make the 6. That is not load balancing. So these 3 can now be split up among the remaining 3, right? Which makes it 4 across each. So this is a very rudimentary example of load balancing. Load balancing does not always need to mean equal partitions of a task or equal copies of a task on all the nodes, right? For instance, I could have one node that is twice as powerful as the other 2 nodes, right? In that case, my load balancing could mean that I run 6 on this, 3 on this and 3 on this. The idea might be that I want to finish on at the same time, right? So now if I run 3 on all, I'm kind of underutilizing this machine. Or even if I do 4 across all 3, I am not taking into account the hardware heterogeneity. So load balancing can be more sophisticated than what you saw, but that's just extra info for your information. But Kubernetes handles breakdowns using load balancing. Will it run the killed operation on another node? Yeah, so when the node goes down, it will automatically make sure that whatever was running is rerun on something else, right? So this is one of the, there are different ways of handling fault tolerance, right? So one way is to redundantly run. So for instance, if you cannot tolerate any latency in something, what you might do is to keep the same thing running, let's say 2 times or 3 times on 3 different machines. So if one of them goes down, you are simply going to switch over to the other machine, right? This becomes a primary in a sense. You could have a primary and 2 secondaries. This is one form of redundancy. The other form of redundancy is if this goes down, you might have some form of a checkpoint, right? For instance, if something happens to your operating system, you might notice Windows has this feature called system restore, where you have a checkpoint at some date or time, and you will be able to restore your system to that screenshot or to that snapshot, right? So you might do something like that and rerun this application from that snapshot. That's also a way of getting it back, right? So these are all different ways of achieving fault tolerance. Hope that helps. Let's move to the next question. Which statement best describes RDMA? Okay, we have an answer B. Okay, everyone thinks it's B. Okay. Yes, that's right. It is B. Capability of HPC network transport layer to directly access remote system memory, right? And I think we already went over this, so we'll skip it. Random access across the cluster doesn't really capture RDMA. Accelerated TCP/IP stack by offloading it to the network adapter, not really. So it is option B. So we'll move to the next question. In a GPU accelerated cluster, what are the most important network characteristics affecting overall system performance? Option A, a balanced GPU network bandwidth that can ensure that data is being fed to GPUs at an optimum rate to keep all processing units busy. RDMA access directly from the GPU high bandwidth memory for efficient data transfer. Use multi-rail connection between GPU accelerated servers with multiple GPUs on board. All of the above. Think about this. I think there's a lot to parse in this question. So take your time and answer. I'll wait for a minute. Okay, we have an answer D. 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 Anyone else? D. Okay, let's take a look at the explanation. So the answer is all of the above, but let's look a little bit into detail on each of these options. So what affects overall, what networking characteristics affect overall system performance? So I think RDMA is an easy one, we've already looked at it. So RDMA access directly from the GPU memory for efficient data transfer. So this was the GPU direct RDMA that we looked at, right? So this would definitely help, because as we saw, RDMA bypasses a lot of things and gives you very high bandwidth and very low latency, right? Very high performance basically. So RDMA will definitely help in terms of system performance. Let's look at C. Use multi-rail connection between GPU accelerated servers with multiple GPUs on board. So again, it sounds a little bit vague, but you've already seen something like that. So if you have a server with multiple GPUs on board, for instance, the DGX is a good example, right? So I think you had 8 V100s or something like that. So you would, by using multi-rail connections, or by using connections that essentially, so the multi-rail could refer to some form of parallelism, right? That would again accelerate your overall system performance. So one would be to use high bandwidth connections like NVLink between the GPUs itself. It could also refer to things like this, multi-rail connections, that again involve some level of parallelism, right? So when you have multiple GPUs on board, the communication between those servers would depend on what sort of connections you use, right? So that again impacts system performance. Now the last one is probably the most nuanced to understand. So let's say the GPU works at a certain rate, right? So the GPU takes certain input images and processes them to give you some output. Now let's say you buy the most powerful GPU that you can get access to, and it has a really high rate, right? Let's say it does 10 power 5 images per second. Again, I'm talking about inference, but this could be training as well, right? It's able to process this much data. Now let's say that my network bandwidth to this, my network bandwidth is not very high, and as a result the input that I am feeding to the GPU is 10 power 3 images per second. Now if the GPU only gets 10 power 3 images per second, even if its peak processing ability is 10 power 5, it will not be able to achieve that, because you are only feeding it 10 power 3. So you are bottlenecked by network, right? So an ideal system would be, or a balanced system would be, one where the GPU and the network bandwidth are balanced, so that the data is fed at an optimum rate to keep all processing units busy. So what happens if you feed only 10 power 3 images to the GPU? It might not, one thing that could happen is it might not occupy all the cores if you are doing this in parallel for some reason. If not, the GPU might finish this set of images and it might wait while you are still fetching that data, right, from the network. So there is some idle time, or the processing unit is idle, it's not busy. So you have to be able to feed data to the GPU such that it is always kept busy, right? So balanced system is one where the GPU and network bandwidths are balanced. So we look a little more into detail at this particular thing, because it's an overall idea that's there throughout systems. So some of you who looked at things like parallel programming might have heard of Amdahl's law, right? That's a very famous one. Broadly, again, let's not go into that here. So this is a different Amdahl's law. It's called Amdahl's other law. It is relatively lesser known, but this talks about architectural balance in terms of compute, memory and IO bandwidth. So compute is represented by flops, memory bandwidth and then IO bandwidth, right? So Amdahl says that the ideal target is 1 byte of memory needed per flop, which is matched by 1 byte of transfer over an external interface. If this is achieved, the computer systems could remain in balance, is what he said. Right? This is known as Amdahl's law. Again, the link from which I've taken all of this is there here, so you can look at this. Now, this is from the hardware side of things. So first of all, the first question you should ask yourself is, how does hardware look today? If I take a ratio of flops to memory bandwidth, does it really look like 1:1? So this graph tells you a little bit about that. So the flops versus memory bandwidth is 4.5x per decade. So the flops is that much more higher. Similarly, if you look at flops versus network bandwidth, it is 9x per decade, right? So you can see the trend that compute is growing much faster than memory bandwidth or IO, or broadly network bandwidth, right? So this, on the hardware side at least, is not true. Now the other question you should ask yourself is, from the workload side, what does it look like? So specifically, since this is an AI course, what does the compute to IO ratio look like for AI workloads? And this, so you know that the system is not balanced. You have a system that is very very powerful computationally, but you're hitting the memory wall somewhere, and similarly the IO or network is also not able to keep up, right? Is this beneficial to today's AI workloads, right? What does the compute to IO ratio look like for these workloads? So again, that's not a question that I will answer, but you can look up this parameter called arithmetic intensity, which gives you a measure of the flops per byte or the flops to IO ratio. So you can take a look at that and see if current day systems are actually designed to run AI workloads very well, right? So this is again something that goes into the crux of building good systems, and how do you get a workload to run efficiently on a particular system, right? So even if you buy the most powerful GPU or the most powerful compute element, you will need to have this part could come back to bite you, or the workload itself, the way the workload is, could also bite you. So it's important to look at the system as a whole, whereas today there is a lot of hype about, oh, this GPU is this powerful and it can handle this many flops, floating point operations per second, right? But that is not all of it. Your IO and your memory access definitely play a role. So that's what this tells you about, and you can read this a little bit more to understand the details. And yeah, another thing I wanted to touch upon, again you'll find a reference here if you want to go through. So latency and throughput, or latency and bandwidth, are terminologies that you will find throughout in a systems course, right? And you might not understand the difference between them very clearly. So I'll give you this example so that that part is at least very, very clear to you. So latency is broadly the time to finish a given task. Throughput is the number of tasks that you can finish in a given time. And these two metrics are often contradictory. So low latency does not mean low throughput, or vice versa, right? So, and which metric do you really pick, that depends on your application or on your goals, right? For instance, with a web server, you might care about throughput, how many requests can you address. With a scientific program, you might care about latency, the time it takes to finish a given task. Now this is the abstract definition as such, but this example will give you a more clearer idea, right? So let's say we are talking about moving people across a distance of 10 miles. Now a car can seat 5 people and drives at a speed of 60 miles per hour. Now a bus can seat 60 people, but it drives at a much slower speed of 20 miles per hour. Now let's look at these two metrics, right? If we look at latency, the time to transport people for 10 miles, how much time does the car take? The car takes 10 minutes. It's 60 miles per hour. You want to move 10 miles. So 60 miles per hour can be taken as 60 miles per 60 minutes. So if you want to move 10 miles, you take 10 minutes. Now let's look at the bus, right? The bus moves 20 miles per hour. So if you do this calculation, you will find that if you need to move 10 miles, you take 30 minutes in the bus. So if you look at latency as a metric, the car is 3 times faster or better than the bus, right? Let's look at throughput. Throughput is the number of tasks in a fixed time. So if you take the fixed time as an hour, how many people are you transporting, right? So the car can only take 5 people, and so if you do this calculation, right, if the car drives for 1 hour at this speed, so the latency is basically 10 minutes, right? So you're talking about 3 trips. So each time it transports 5 people, so overall it transports 15 people. Whereas if you look at the bus, each time it transports 60 people, and over an hour, I think you count return trip here, I'm sure you guys can work this out. Overall, the bus transports 60 people per hour. So you can see that the car gives you, so latency wise, lower is better, right? You're looking at execution time. Throughput is the number of tasks that you execute, so higher is better. So the bus has a higher throughput. So bus is 4 times faster than the car. This is just some formula, you can ignore that, but this gives you a very practical example of how they are also contradictory, right? Something that has a low latency need not always have a high throughput. Similarly, something that has a high throughput need not have a low latency, right? So keep this in mind whenever you come across latency and throughput, and that will help you understand them better. Okay. Which is not the correct mechanism to increase network bandwidth on the physical layer? Increase the clock frequency, increase transmission amplitude, increase the number of physical lanes or channels, use advanced modulation scheme like PAM4. Any answers? D. Okay, advanced modulation. Anyone else? Think about these. Again, it's not a very obvious answer. Think about it. You've studied about many of these things. Someone else says D. Okay, B, transmission amplitude. Okay. Any other answers? B. B, A, lots of answers, lots of different answers. Anyone else? Okay, let's look at the answer. It is B. So let's look at this diagram, right? Some of the things that we discussed were complex modulations and different things with respect to the physical channel and things with the line rate, things along the wavelength channel, right? But now let's think about this particular question. Which of these will not increase network bandwidth, right? Now if I increase the clock frequency, I'm essentially sending more data, right? So that would increase the network bandwidth. Let's look at this: increase the number of physical lanes. So this is like sending things in parallel, a very simple analogy. This is sending things faster, this but in the same serial sequence. This is sending things in parallel, right? So this again increases the bandwidth. Now let's look at this. This requires a little more nuance. So pulse amplitude modulation, as we discussed previously, uses different levels for different values. The amplitude itself has different levels. Now what does this mean? So in that case that we saw, we said this was starting with 0 0 and this went to 1 1. So in a given pulse I can transmit 2 bits as opposed to 1 bit that I used to do with your typical return to 0 or non-return to 0, right? So this is again a way of encoding more information in a given digital pulse, right? So because you're modulating the amplitude of the signal itself, at the demodulation side, depending on that value that you see, let's say this is 4 volts, right, the third one. So if I get 4 volts, for that same single pulse that you are sending, I am able to get 2 bits of information, right? So that's one of the reasons that it increases the network bandwidth. Now think about if I just increase the transmission amplitude. So this is not sending more information, it's not sending things faster, it's not sending things in parallel, nor is it sending more information per pulse. This will probably only help with something like signal to noise ratio, so the attenuation you see might be lesser, but other than that, so broadly this affects the range but not the information capacity, yeah, or the bandwidth, right? So this is the wrong answer, or which is not the correct mechanism, is the transmission amplitude. So this is a little complicated to understand. So is this clear? Any further doubts? Okay, if not, yeah, great. Let's keep moving. We have 10 minutes left. Which technology improves the performance of MPI operations? Shield, Sharp, multi-host technology, socket direct technology. B, Sharp. B. Anyone else? B. Okay, everyone is clear about this. The answer is B, Sharp. We already looked at it. So doing things like reduction and aggregation in the network element itself is definitely beneficial for MPI operations and improves its performance. Shield was the resilient / self-healing network. Multi-host technology gives you some of these things you might not have seen in the slides or in the course material itself. I've just added it here in case you're curious. Direct connectivity from multiple hosts to the network. Socket direct enables direct PCIe access to multiple CPU sockets. So Sharp is the only one that's improving performance of MPI. Hope this is clear. Let's keep moving. The number of nodes in an n-dimensional hypercube network is dash. So again, take a minute to think about this. It might not be very obvious. D, 2 power n, okay. Anyone else? d 2 power n Okay. Any other answers? Is it like square, cube, and we'll take a look at that. Okay, let's look at it. So again, this is not there in your slides, so I've picked this up from a textbook and I've given you the name of the textbook. So the answer is D. Sorry, I've not highlighted it here. But so we were asked about an n-dimensional hypercube. So let's start with a 0D hypercube. This is what it looks like, right? A one-dimensional hypercube. So this is how you construct these from lower dimensional ones. So it's constructed from two 0D hypercubes by connecting them. A 2D hypercube of 4 nodes is constructed by taking two of these and connecting them, right? And then if you have a 3D hypercube, you connect two of these together, right? Which is what you see here. Now, as you can see here, so in general, you can also see this for a 4D hypercube in the textbook. You can look at this figure, but it was too complicated, so I have not gone into that. But again, as you see, a 4D hypercube has 16 nodes. So in general, an n-dimensional hypercube will have 2 power n nodes. So that's the answer to this. So you can verify that for all of these, right? 1, 2 power 0, 2 power 1 which is 2, 2 power 2 which is 4, 2 power 3 which is 8, and 2 power 4 which is 16. Okay, but glad all of you got that answer right, even though it was not part of your slides. So let's move on. Which among the following statements is or are true about InfiniBand? InfiniBand is the only architecture that can be used on the PCB. It has unicast and multicast support. High priority transactions between devices can be processed ahead of the low priority items. So you have options that are combinations of these. Okay, we have answers saying C. Okay, all three. Anyone else? C. Okay. Anyone else? C. Let's take a look at the answer. It is C, which is all three, right? And this InfiniBand was not at all discussed in the slides, so I don't think we can go into the details of any of these, right? So it's more about, so this is the primary reference for InfiniBand. It's a white paper and it's available here, but this is a really long white paper, so I don't expect any of you to read it from end to end, but you will find details about all of these in the white paper. But it's out of the scope of this course for us to go into the details of how these things happen or why these happen, right? So for now it will be sufficient for you to know that InfiniBand supports all of these things. If you are curious, you can go take a look at this. I will leave it at that. Let's move on. What are the three levels of Dragonfly network topology? And you have three options. Okay. We have answers saying C. C. Anyone else? Okay, I think everyone thinks it's C. So it is C. It's router, group, and system. Again, I've given you a link where you can, this again like a news article, right? So it's very easy to read. So you can read about all these topologies: mesh, torus, dragonfly, all of these a little in detail. But since someone specifically asked about dragonfly today, I'll try to see if I can find a very easy way to understand the entire topology. But broadly, it is a hierarchical network topology with three levels, right? A group, and then the whole thing as a system, and then routers. So those are the three levels in the hierarchy. Okay, let's move to the next question. Which among the following are true? Zero copy networking does not utilize the computer processor. Data transfer between systems without RDMA is faster than systems that enable RDMA. iWarp is not compatible with RDMA, both A and B. A, A, okay. Anyone else? D, both A and B. D. Anyone else? Let's take a look at the answer. So zero copy networking does not utilize the computer processor is true. So let's look at the others before that. Data transfer between systems without RDMA is faster than systems that enable RDMA, which is not true, right? This is faster. iWarp, what is iWarp? It's a networking protocol that implements RDMA over internet protocol networks, right? So this is again false. So looking particularly at zero copy networking, so this is again, maybe this couple of points is not very intuitive for you to understand. So I'll talk a little bit more about the zero copy part of RDMA. But again, like RDMA itself, the idea is to bypass the CPU as much as possible, just like DMA, right? So if you've not studied DMA before, you should start from there, because RDMA is just a logical extension to that. So it tries to keep the CPU utilization low, right? So zero copy networking does not utilize the computer processor is true. So this is the right answer to this. Okay, I think with that we are at the end of the session, right in time. So I will take up the few doubts that were asked today in the next session, since we don't have any more time left. If you have any other doubts or questions, please post them on chat. I'll stay here for a minute more. So please take this time to post your questions and doubts. If you don't have any doubts or questions, thank you so much for participating and being here today. Hope this session was useful to you. And if you have any feedback for me, please leave that in chat as well. And see you in the next live session. Thank you so much. Thank you. Thank you. Any last questions? If not, feel free to drop off.